Let's take a look at practice question set number 29. Talks about this artificial transmutation of one element into another by directing alpha particles. And we never talked about this specific form of artificial transmutation, but that's okay. Okay, in the end, we can still answer the question. It says the new unstable nucleus formed in the artificial transmutation is what? Well, it says beryllium-9 is struck with the alpha particle, so we're going to say beryllium, I think is Be, right? Beryllium-9, what's the atomic number for beryllium? Where are we going to find that atomic number? On your periodic table. What is it? 4. It's bombarded by an alpha particle, so we're going to say 4,2 alpha is on the left-hand side. This would be not alpha decay. Alpha decay would have the alpha particle on the right-hand side because it's decaying into an alpha particle. This is being bombarded by an alpha particle, so it becomes part of the reactants or the parent nuclei, you could say. It emits a neutron, so there's a neutron and a stable nucleus. What's that other stable nucleus? Well, we say on the left-hand side, 9 plus 4 is 13, 4 plus 2 is 6. So we have 13, 6 on the left-hand side. We have to have 13, 6 on the right-hand side. 1 plus 12, 0 plus 6, that would be carbon. Carbon 12 would, what's wrong here? What did I do wrong? Beryllium-9, struck by an alpha particle. Oh, look at that. Oh, I didn't read that carefully. Good thing they didn't have an option that said carbon 12 there, right? What did I do wrong? What did I mess up on when I was not careful? It says here beryllium-9 is struck by an alpha particle. It produces an unstable nucleus. The new unstable nucleus that's produced as a result of that emits a neutron and then a stable nucleus. So we have this happening, right? Beryllium plus the alpha particle goes to something which goes to a neutron and carbon. Does that make sense? What did I find? I found the new stable nucleus. It's not what I'm looking for. I'm looking for the unstable nucleus. So the unstable nucleus would say 9 plus 4 is 13, 4 plus 2 is 6. That would mean it would be carbon 13. We would know that it would be carbon 13 as opposed to boron 13 because carbon has an atomic number of 6. Boron, I'm not sure what it is, but it's not 6. So we know that it can't be boron. Does that make sense? All right, now let's identify the physics principle used to determine the atomic number of the stable isotope is conservation of what? To determine the atomic number of the isotope. So to determine this, what are you going to use? The law of conservation of charge, right? Because we're adding up the charges, the number of protons here. 4 plus 2 is 6. So the answer would be D. By the way, conservation of nucleons is something that you could use, but conservation of nucleons you would use to find the mass number, not the atomic number. Does that make sense? So it said, how did you find the atomic number? We're going to say conservation of charge. It said, how do you find the mass number? We're going to say conservation of nucleons. Because a nucleon, you remember, is a proton and or a neutron, right? And that's what the mass number is. So the answer is D. 2, if the new unstable nucleus is at rest when it decays, and then the recoil speed of the final stable nucleus is what? And what conservation law do we use to analyze this? Hopefully something jumps out at you here. We've got this nucleus that is at rest, like this, and then a second later, we got something going this way and something going this way. What is that? I'll give you a hint. It's been a while. It's momentum. That's a conservation of momentum problem, right? That's an explosion. Like those questions in Unit 1 where we fired a gun and the bullet went one way and the gun went the other way. Or a bomb exploded on a table and one piece went this way and one piece went that way. It's exactly the same thing. Just because we're dealing with atomic physics now doesn't mean we can't use the law of conservation of momentum. So let's say for this one, Pi equals Pf. The initial momentum of the unstable nucleus is 0 because it says it's at rest. The recoil speed of the final stable nucleus, well, we've got two objects afterwards, m1v1f plus m2v2f. And it says in the information up there, somewhere, it says in the information up there, the neutron is emitted with a speed of 2.18 times 10 to the 7. We're going to call that mass 1. The neutron is 1.67 times 10 to the minus 27 times the final speed or the final velocity of that neutron, which was 2.18 times 10 to the 7 meters per second. Plus the mass of the final stable nucleus, which we're told is 1.99 times 10 to the minus 26. Times V2F. When we solve for V2F, I want to say we get 1.83. Is that right? Is it 1.83? Okay, so the answer is either going to be C or D. Would actually be negative, right? 1.83 times 10 to the 6. But remember, we got a negative velocity, but what are they asking for? They're asking for the speed. So, of course, we're going to get a positive number for the final answer, right? 1.83 times 10 to the 6. And, of course, doing what we just did, we know that it's the law of conservation of momentum that helps us to determine that. That's a great question. Love that question because it's this unit on atomic physics, but it also ties it into like almost the very first thing we did this year. Don't think that just because you're dealing with a nucleus that you can't do something that we did earlier on. Just like when we did the cathode ray tube and we were talking about electrons deflecting in the main chamber of the cathode ray tube in a circular path. That was really back from our magnetism unit, right? Just because it's a different context doesn't mean we can't do that stuff that we learned a while ago. So if you have an explosion, no matter what the context, whether it's a bomb literally exploding or a gun being fired or a nucleus decaying, we can still use the law of conservation of momentum. 3, gamma radiation is chosen for food irradiation because, anyone? It's a safe, low-energy radiation? No, definitely not. Definitely not. Is the easiest form of radiation to produce? Definitely not. What would be the easiest form to produce, probably? Like, I mean, you could argue that that's a matter of opinion, right? Which is the easiest to produce. Just like, you know, somebody says, what's the easiest unit in physics 30? Unit 1, unit 2. Well, that's a matter of opinion, right? But I would suggest probably the easiest type to be produced would be radio waves or microwaves because it's produced by alternating charge. It seems to be easier to alternate charge than it might be to accelerate electrons to crazy high speeds and then smash them against a target to produce X-rays, or easier than using nuclear decay. Gamma radiation would not be the easiest form of radiation to produce, certainly. It penetrates into the food through its packaging. Yeah, gamma radiation has a really high penetrating power, right? So that might work. Okay, that seems to be a pretty decent answer. Let's just take a look at D to make sure there's nothing better. Because remember, it isn't choose the correct answer, it's choose the best answer. Usually there is one correct answer, but sometimes there's a couple that could work, but one's better. Poses no danger to the technologist doing the irradiation. Well, no, it poses a danger, so that's definitely out. That means the answer's got to be C. Here we're talking about decay of radium-223 producing alpha particles, double alphas, which is beryllium-8, and even triple alphas, which is same as a carbon-12 nucleus. 600 days, this many alpha particles. What do we got here? Which of the following initial products is observed in the greatest abundance? Which would be produced in the greatest abundance? How are we going to tackle this? What does it say in paragraph 2 here? Not the 600 days thing, because this is not a half-life calculation or anything like that, right? We detected 10 to the 10 alpha particles, but no double or triple alphas. So in other words, we're undergoing mostly alpha decay, right? Regular alpha decay. So if we say radium-223, is radium 88 or 86? 88? Okay, radium-223 undergoes alpha decay because that's what we detected the most, right? So what are we going to be left with? The most? We're going to say 4 plus 219, 2 plus 86. I think that ends up being radon. Radon 219, so my answer would be A. Which of the following products was not predicted by Rose and Jones? So here we're going to say, let's say we start out with radium-223. Radon-219 was predicted, right? So that's not going to be an answer because that was predicted. Right? In fact, that's what we get the most of. Radium-223, let's say we're producing a double alpha. It's beryllium-8. I think that's atomic number of 4, isn't it? Yes? Plus, what, 223, 8 plus 215, 4 plus 84. I assume that's polonium. Is that polonium 2? It's atomic number 84? What do we got here now? Transmutation reaction where nitrogen gets bombarded by an alpha particle, unstable proton, and then something else. What's the value of A and Z? What's the value of A and Z? All right, so let's write this out. We got 12, 7 nitrogen plus 4, 2 alpha goes to, what's that going to be, 16, 9. What's 9? Doesn't really matter, but what is it? Fluorine. The symbol is F. Goes to a proton. Proton is 1, 1, right? 1 proton, 0 neutrons, 1, 1. Plus, what do we got here? 1 plus 15, 1 plus 8. That's going to be oxygen, I think, isn't it? Although it doesn't really matter. 15 and 8 is my answer, I guess. You got to be careful with a question like this. I made a mistake on a question like this one time because, again, because it wasn't reading carefully. It was something like, I can't remember what the symbols they used were, the notation they used were, but it was like, let's say they called this, they didn't call it A and Z, but let's say they called it A and Z. They said ZA, and then what are the values of A and Z? So what happens? If we're not careful, what happens? We write the answer backwards, right? That make sense? So be careful of that, right? Now, these are the standard symbols for this. So in this context, we shouldn't see something other than A and Z. But if they happen to ask you for the values of Z and A, you just got to be careful that you list it in the right order, right? Yep.
With the term unstable nucleus.
Now it looks like we got another transmutation thing here. My guess is when we look at this that we're probably going to be dealing with finding A, B, C, and D. Let's take a look at the question here. In the nuclear reaction above, the values of A, B, C, and D are what? All right. That doesn't look like it's too hard. 4 plus 23 is 27. 2 plus 11 is 13. On the right-hand side, we've got 1 plus 26, 1 plus 12. So we've got A, B, C, D is 2, 6, 1, 12. 2, 6, 1, 12. I want everybody to take a look at their data sheet for just a second, please, okay? We're going to talk more about what I'm about to mention to you next week. We'll spend about a half an hour going over this, just the idea of this, the technique of this. But you will get at least one question on your exam. It's probably going to be the last one, question number 50 on your exam, where you're given a numerical response question that you have to solve like we just did, and then you're going to have to identify in the follow-up question to it, the following question, the 2 physics principles that you used to answer it. Now, what would the 2 physics principles be that I used to answer this one? Even though we're not asked to identify the physics principles. How do you know which physics principles to pick from? Bottom left-hand corner of your data sheet, it lists a bunch of them. And again, we'll talk more about this next week, these physics principles, okay? But it's a perfect question to kind of introduce this idea to you. In order to determine 2 and 6, the mass number, I used physics principle number, what would it be? It would be 8, conservation of nucleons. In order to determine the 12, the atomic number, I used principle number 7, conservation of charge. That's right. So the follow-up question to this would have an answer of 8, 7. Does that make sense? The 2 physics principles used to answer that previous question were principle 8 and 7, and then we would leave the last 2 blank. Okay? 7. In the nuclear reaction equation above, element X is what? Oh, element X, all we got to do is look at our periodic table and determine what atomic number 12 is. What is atomic number 12? What is it? Magnesium, somebody said? So the answer would be B for that one. And when the signals are sent to Sojourner, the distance between Earth and Mars was what? We want the distance between Earth and Mars. We have, well, we know the speed is 3 times 10 to the 8. We know the time that it took was 10 minutes. So we're just simply going to rearrange that. You get d is equal to v times t. Our speed of the wave is 3 times 10 to the 8 meters per second. Regardless of whether it's radio waves or gamma rays or visible light, 3 times 10 to the 8 in a vacuum times 600 seconds, because of course we want seconds, not minutes. 3 times 6 is 18. So we get 1.8 times 10 to the 11, is it? 1.8 times 10 to the 11 meters, which we would express here as 1.8 times 10 to the 11 meters. Let's follow that up with practice question set number 30 here. We start off with a decay curve. You know what? In all likelihood, we're going to see a decay curve on our unit test next week, and in all likelihood, we're going to see one on our diploma exam as well. And that's good news, because when we see one of these graphs, we know we don't have to do anything crazy with it, like the whole y equals mx plus b thing and so on. It's not a straight line. We can't make it a straight line easily. Physics 30, we can't make it a straight line, period. So we just have to remember that it's up and over and down, whatever. Depends on what we're trying to find here. What are we trying to find here? The time required for 40 gram sample to decay to 1.25 grams. 40 grams to 1.25 grams. There's a couple ways you can tackle this. Okay, a couple ways you can tackle this. We could say the half-life. We could find the half-life to go up by going over and down. So 50, start with 100%. After one half-life, we get 50. Go over and down. Looks like the half-life is 6 hours. Right? Half-life is 6 hours. Does that make sense? Or 0.6? Yeah, 0.6. That wouldn't make sense. Does that make sense? And then what could we do with that? Yeah, you could put it in the formula and solve for t. That wouldn't necessarily, if I could avoid using the formula with the graph, I would, because sometimes data points on a graph aren't perfect, and a formula assumes perfect, right? Having said that, usually in these graphs, especially if it's just the line and not points, it's pretty safe to assume that that would be okay. Okay, but if we can avoid it, we would probably want to avoid it. Is there any way to avoid it in this case? Is there anything else we could do? Yeah? What'd you do?
Well, there's 26 in an hour, so, and it's 5 half-lives, get from 40 to 1.5, so 5 times 3.6.
Yep. Yep, so 3 hours. So at 3 hours, we're going to go up and over. The problem with that is that it's pretty difficult to determine Oh, no, sorry. Yeah, sorry, no. No, I'm doing that wrong here. You end up getting 3.0 hours, and it's a 2-digit answer, so we would record it as 3.0. Next one. Maximum percentage of technetium 99 that could be still present 24 hours after injection is what? The half-life is 6 hours, so we're going to say the number of half-lives is 4. 24 divided by 6 is 4. And we're going to say that we started with 100%. (100) times 1/2 to the 4 would give me 6.25, I think, isn't it? 6.25%. A photon has, oh, this is different because this is back to last unit again, right? Energy of a photon. We want to find the wavelength of the photon. We're just going to say E is equal to hc over lambda. Remember that? From before Christmas, from my last unit test, hc over E. Since we've got the energy in electron volts or mega electron volts, we're going to say 3.85 times 10 to the 6 electron volts and use the value for Planck's constant of 4.14 times 10 to the negative 15. What do we end up getting there? Which one is it, A, B, C, or D? B. 3.23 times 10 to the negative 13. And last one, finally. Experiment starts with 1.45 kilograms of iodine-131, 32.2 days. This is much is left. What's the half-life? So let's say N0 is 1.45. N is, let's say, 0.0906. This is kilograms, right? Got to be in the same units. It doesn't matter whether you're in grams or kilograms, but you've got to be in the same units. We're just going to say T is 32.2, and we're looking for the half-life here. So I'm going to say N is equal to T over T 1/2. I don't know what little n is. Who's one of our logarithm people? Who's our logarithm people? Who's our divide by 2 people? All right, one person's a logarithm person, one person's a divide by 2. Okay, boy, I hope we don't get a question like this on our exam because only 2 of you are going to get it right, apparently. I'm going to go the divide by 2 method, okay? We're going to start off with a table, little n and big N. After 0 half-lives, we've got 1.45 kilograms. After 1 half-life, what is that divided by 2? 1.45 divided by 2. What is it? 0.725. Then we're going to divide that by 2. So after 2 half-lives, we end up getting 0.3625. After 3 half-lives, 0.18125. And after 4 half-lives, we get 0.0906. And then we got a 2.5 after that. So we got 4 half-lives. We're going to say the time here is 32.2 days divided by 4 half-lives. Gives us 8.05 days. Our answer would be C. How many people got that? How many people used logarithms? So when I said, who are my logarithm people, where were your hands then, huh? How many people use the divide by 2 method? You guys.